Okay. So you should now be able to see a blank page. I seem to have lost my my participants list. I mean my chat list. Okay. Sorry guys, I'm just trying to sort this out on my laptop, which is pretty tiny and dicky. Okay. So I thought we'd start off with just a bit of background around about what was happening in mathematics around about the turn of the 20th century. So turn of the 20th century, we've got an increasing level of sophistication in thinking formally about what exactly logic is and what a logical deduction is, and some things happening in maths as a result of that. So one thing that happened in maths was that they tried to do the kind of thing that Euclid had done with geometry in other parts of maths. That is, give a set of axioms, that's basic sort of self-evident truths for other parts of maths, and then the thought being that you could then use those truths to deduce all the other truths in that area of maths, as Euclid did with geometry. So here's a thought. One a very useful structure in maths is the set. So they decided to try and do what Euclid had done with geometry with set theory. And an easy way of doing that is just to say, well, actually set theory is pretty simple. There's an axiom that says that you've got to define what it is for two. Oh, no, there's just nothing much happening on the screen. Can you see naive set theory and the two axioms? Hello? Good. Okay, so one thought is, sets are pretty basic to mathematics, so let's axiomatize set theory. So the first thought was, well, there's a famous saying in philosophy, no entity without identity. If you want to talk about something, you've got to say what it is to recognize it again. So you say two sets are the same. It's called the axiom of extensionality, if and only if they have the same elements, basically. For all x, the upside down A here means for all. So, and the two arrows mean if and only if, the arrow's going both ways. So formally, two sets A and B are equal if and only if for any element x in A, that is an element of B. Makes sense? And the other axiom was, well, what is a set? Well, it's just you give me a property, say red, and that's a set, the set of all red things. So for any property, there's a set of objects, the set of the set that has only the elements whose elements are all and only those things that have that property. That's called the axiom of comprehension. Formally, the upside down A here means for all x. For all x, x is a member of set A if and only if x has property P. Beautiful, eh? Lovely. And so a thing to notice here, a lot of people on the report and in the test said that Hilbert was after finite sets of axioms. He wasn't. Most interesting mathematical areas of maths need to have infinite number of axioms. So you notice here, naive set theory in a way has two axioms, but really it has an infinite number of axioms, because the second axiom, the axiom of comprehension, isn't really an axiom, it's what's called an axiom scheme. Namely, it's a rule for creating axioms. And the rule says that you can, for any property P, you can include an axiom about that property, namely that there's a set which has as elements all and only those things in the world that have property P. So the axiom of comprehension isn't one axiom, really. It's an axiom scheme that allows you to have as many axioms as there are properties. Arguably, there's an infinite number of properties, so there's an infinite number of axioms. So what Hilbert was after was what's called a finitary set of axioms for mathematics, where finitary isn't finite. Finitary means that you can systematically elaborate all the axioms. So here, if you had a list of all the properties, then you would be able to systematically elaborate all the axioms. Namely, for each property on your list, you'd create an axiom of comprehension for that property. Okay, so here's the thing. There's a problem. Lovely pair or set of axioms there for set theory, but consider this set. The set R that has as elements all those sets that are not elements of themselves. So R is the set of X's, elements X, where X isn't an element of itself. Now, according to the naive axioms of set theory that we just looked at, R is a well-defined set. It's just what we'd call a substitution instance of that comprehension axiom schema, where you put R for A in the schema, and you put the property X isn't a member of itself in for the property P of the schema. Can you see how that that set is just something you get by substituting R for A, and X is not a member of itself for P, Px into the axiom of comprehension. Yeah, it's Russell's paradox. Or Russell's a paradox is a contradiction that doesn't feel like it should happen. So it's a contradiction, but it's a paradox because Russell felt it shouldn't happen, because it seemed like set theory should be consistent. I mean, we're talking about sets here. It seems like they're almost, sort of common or garden objects. And, you wouldn't expect there to be a contradiction about the objects in your backyard. And if you think that sets are sort of like abstract objects, much like the objects in your backyard are concrete objects, then you wouldn't expect there to be a contradiction about sets. But here there is, because you can define that set, the set of all elements, the set whose elements are themselves sets who don't contain themselves. And, oh no, if R is R a member of itself? Well, if it is, it isn't, and if it isn't, it is. Might need to think about that for a little while to see that that's pretty frightful, because it comes down to being equivalent to saying R is a member of itself if and only if it isn't a member of itself, which is a contradiction. Another equivalent way of saying that would be R is a member of itself and R isn't a member of itself, which is more clearly contradictory. So, look, I thought I'd just introduce that to give you a very clear idea of what Hilbert was freaking out about, because that's terribly embarrassing for mathematicians, isn't it? Mathematicians see themselves as working a way to find out all these truths about mathematics. But if you find a truth, you don't want some other mathematician working somewhere else to find out the exact opposite of your truth. That if you find out that if you prove that all triangles have internal angles that add up to 180 degrees, you don't want some other coot on the other side of the world to publish a paper that proves that all triangles No triangle has internal angles that add up to 180 degrees. So it's very embarrassing. So what to do about it? Well, that's where we get on to Hilbert and his program. So Hilbert's program, the thought was to try and eradicate this sort of thing happening. To give collections of axioms from which we humans could deduce all the truths of maths, where you want those collections of axioms to be finitary, not finite, but finitary. That is, there could be an infinite number of axioms, like there was in the case of the naive axioms. But you can produce those axioms systematically so that if you follow some procedure, you'll always get the axiom you want eventually. And you could have a little machine that churned out the axioms, and you'd know that any axiom would eventually appear. You might have to wait a long time, but it would always get there. You could, given any purported axiom, you could check whether it was or was not an axiom. So it's decidable. You might like to think about that sort of procedure with reference to numbers. The positive integers, you can systematically enumerate them. You can produce one after the other. You can set a machine up that'll just boom, boom, 1, 2, 3, 4, 5, 6, and any integer will eventually come out. Eventually. But the reals, you can't do that, yeah? If you set a little machine up to produce all the reals one by one, boom, 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 it wouldn't get anywhere because there's an infinite number of reals between any two reals. You could set a machine up to produce all the reals. Nah, no. You couldn't even do it for all the rationals because it's dense. Between any two, there's an infinite number of other ones. It's sort of like I was going to say Zermelo, Zeno's paradox. The arrow will never get to the wall because it's always got to get halfway to the wall, but then it's got to get halfway to halfway, and it's got to get halfway to halfway to halfway, and so on. Okay, so finitary is a bit like the integers. You can do it. You can get all of them by systematically churning through. Well, you never get to the end, but for any particular integer, you can eventually get there. But it's not finite. He also wanted them to be consistent, of course. That means he didn't want the sort of thing that happened with naive set theory to happen. He didn't want it to be that you could both prove a theorem from the axioms and prove the opposite of the theorem, the negation of the theorem from the axioms. That would be awful. Terribly embarrassing. And he wanted them to be complete. That is that you wanted an set of axioms that was enough. There are all the axioms you needed so that you could show any particular truth of maths. You could prove all the truths of maths from the axioms. Okay, so there's a few things going on there, isn't there? There's the finitary bit, the thought that you could actually, a human could actually check all the axioms, find all the axioms, any particular axiom they needed, and check any purported statement to make sure that it was an axiom. And then there's the consistency thing and the completeness thing. So is everybody clear on why those three criteria would be the sort of thing that you'd want from an axiomatic mathematical program? Any questions? Okay, I'll move on. So the thought here is it's about, for Hilbert, back then, it was before computers, so it was about what humans could do given enough time, or what humanity could do. So maybe not this generation, but the next or the one after that. Once we've got the axioms, it's just a matter of people getting there with their pencil and paper and writing out proofs and slowly pushing forward the boundaries of mathematics. So the thought there is what humans can do with pencil and paper by just systematically producing proofs that might be spoken of as being systematically or effectively enumerable. So suppose you had a particular statement in mathematics. You could have one lot of mathematicians trying to prove that it was true, and another lot of mathematicians trying to prove that it was false. And eventually, one of those groups of mathematicians would come up with a proof. So in the end, maybe after many generations, but eventually, the statement would be either proven to be true or proven to be false, if your axioms were consistent and complete. Okay, so so long as you have a logical system, so a way of deducing truths from other truths that is systematically or effectively doable, so there's a finite number of rules that you can use, that would render maths decidable. So the question really becomes, well, one of the first questions is the actual process of producing proofs something that can be done systematically and effectively so that all of the proofs will eventually be produced? Well, like the integers, so that you can work through it so that you know that any particular proof will finally come up, even if it's after a very long time. That's what's known as the Entscheidungsproblem, which is just German for the decision problem. Okay, so the thought is that in order to, this is the move from mathematics into the basics of computation, if you like. In order to get a really clear grasp of what Hilbert's program involved and to check whether its goals were achievable, the first step is to get far more precise about what exactly systematically or effectively doable means, yeah? Because at the moment it's just a vague idea that, if mathematicians sit there writing out proofs according to the rules of logic, starting with the axioms, the hope is that they'll come up with any particular proof eventually. But to check whether that's actually going to be the case, you need to get far more systematic about what exactly a mathematician can achieve just by following the rules of logic and using the axioms. So that's where the Turing machine comes in. Also, Church's lambda calculus and Gödel's recursive functions. They're all attempts to get a more systematic handle on what exactly was possible just by a human sitting there with a pencil and paper and following a set of rules. Turns out that they're all the same, yeah? That you can prove that the set of Turing machine decidable functions is the same as the set of lambda definable functions is the same as the set of recursive functions. So although the idea of what exactly effectively or systematically calculable means is sort of vague, the fact that these three separate attempts by an Englishman, an Italian and a German, as it so happens, all coincided, gives you some extra faith in the thought that maybe they did capture what it is that a human working systematically can do with these three formalisms. So that's the Church-Turing thesis, yeah, that these formalisms do capture what it's possible for a human to do working away systematically. But you can see, I think, that it's not really this, it's a thesis that you can never give a rigorous proof for that thesis, because what you're trying to do is capture a fairly vague notion, what a human can do using a pencil and paper, by a very precise notion. So the only thing you can say is that the fact that these three all turned out to be the same gives strong evidence for it, as does the thought that nobody's ever managed to show that a human might be able to do something that none of these machines can do. Everybody happy? No questions?
Not really. But isn't the Turing machine in order to disprove Hilbert's program?
Yeah, but before you could disprove Hilbert's program, you had to be more exact and mathematical about what exactly the program was trying to do, yeah?
So the Turing machine lambda calculus, a Gödel recursive function, is trying to explain what Hilbert program to do and then disprove it.
Yeah, you got it. Well, it turned out they could disprove it, but the first thing to do was to get quite clear on what the program was. So Hilbert was saying, well, we want, to be able to, a human to be able to check that the axiom's purported axiom really is an axiom, and to, be able to produce any axiom they want eventually. And we want them to be able to get all the proofs systematically by working away with a pencil and paper. That's all pretty vague. Then Turing says, well, all of those things, if they're doable by a Turing machine. So that gives it a much more precise definition that you can actually start proving things about. Okay. So of course, as soon as they gave it a precise definition so that they could start proving things about it, oh dear, they start proving things that suggest that Hilbert's program is not achievable. So the first thing that came up was the halting problem. Hilbert defined the Turing machine and then proved that you can't actually have a Turing machine that can check any other Turing machine to see if it will halt on its input tape or not. So what does that mean? Well, that means that I don't want to go too much into what a first order system is, but basically when you're looking at logic, you can say, for all numbers, for any number x, blah, 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 blah. And that's what's called a first order universalization, because you're talking about for any, but you're only talking about numbers. Or you can say for any set, but if you're talking in set, for any element of a set. But if you start talking about properties and you say for any property, blah, 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 that's second order. So second order systems turn out to be horrible. So they were trying to keep it down to first order systems. Anyway, the halting problem amounts to showing that not all first order logical systems are decidable. So just because you've got logic and you've got a set of axioms doesn't mean you've got a decidable system. Basically because you can put Turing machines into a first order logical system, and the halting problem shows that there's an undecidable question you can pose in that system, namely whether or not Turing machine X will halt. So it's not going to work all the time, Hilbert's kind of idea, but maybe the thought was, well, maybe it will still work for the important parts of mathematics. Sure, it can't work for everything. You can't just have any old set of axioms about anything, about Turing machines, say, and they'll be, you'll be able to use those axioms to prove all the statements you want to are true and none of the statements you don't want to are true. That's not always going to happen, but maybe it still is going to happen for the important ones. Then Gödel comes along with his. There's another thing that I think Gödel's theorems aren't specifically on the study design this year because of COVID, but it's good to get clear on them anyway because they are the sort of endpoint of all of this stuff that you're studying. There's actually 2 incompleteness theorems from Gödel, yeah? I don't think I saw one paper that acknowledged that. Everybody talked about Gödel's incompleteness theorem. There were 2. And before that, he had a completeness theorem, but that's another story. The first incompleteness theorem of Gödel's was basically he managed to tuck the whole of proof theory inside of a very simple form of arithmetic. He gave numbers to all the symbols, and then he could give numbers to all the statements, and then from that he could give a unique number to every series of statements, which is what a proof is. So he could actually tuck the whole of first order proof theory inside arithmetic. So he could have a statement of arithmetic that said, I am not provable in arithmetic, because he tucked all of proof theory into arithmetic by giving everything numbers. So it's a bit like the Russell's paradox or the liar's paradox, because you've got this statement now of arithmetic, or that's translatable into arithmetic, that says, I am not provable in arithmetic. So if that statement's true, then it's a statement of arithmetic that's not provable in arithmetic. And if it's false, then it's a statement of arithmetic that's provable in arithmetic, but it's not true of arithmetic. So either way, you've got a problem. Hopefully, it's a statement that's true in arithmetic. So in that case, it's a statement of arithmetic that's true, but it's not provable in arithmetic, in first order arithmetic. So Gödel's first incompleteness theorem says that in any consistent first order logical system that's strong enough to include natural number arithmetic, there's a statement that can't be proved or disproved by that system. So it's saying that first order arithmetic can't be complete. Because remember, completeness was about being able to prove all the truths of maths from your axioms. It turns out, well, you can't for any kind of system that includes arithmetic. So the consequence of that is that the decidability doesn't seem to be achievable. Remember, the Entscheidungs problem said, well, decidability is not a given for any logical system with axioms. Now it's worse. Decidability doesn't seem to be possible for a system of arithmetic, an axiomatic system of arithmetic. So, whoops, you might be able to prove some of the, or most of the truths of arithmetic, most of the important ones, but you can't prove all of them. Any questions about that? Nope. Okay. Then Gödel kind of, he wasn't, content with just pushing Hilbert over. He kicked him while he was down too. The second incompleteness theorem says that it's not possible for any first order logical system strong enough to include natural number arithmetic to prove its own consistency. So the incompleteness theorem says that there's going to be some truths of arithmetic that you can't get proved from first order arithmetic axioms. So you're not going to be able to get everything. The second incompleteness theorem says that not only that, you can't prove that you won't get contradictions from within arithmetic. You can't use arithmetic to prove that arithmetic itself is contradiction-free. It turns out you can use stronger systems, but the stronger systems aren't what Hilbert would call finitary. They have to use infinities that are bigger than just the infinitude of the natural numbers. Just going beyond our course by a long stretch. So it's not that arithmetic's likely to come up with paradoxes or contradictions. It's just that you can't prove it won't using arithmetic. And given Hilbert's idea of finitary methods, not finite methods, but finitary, that is, methods that just plonk along, check one thing after another, and will eventually get there, which is sort of like the natural numbers. It turns out that those sort of methods aren't going to be sufficient to show the consistency of arithmetic. So you've got, boom, no interesting mathematical systems likely to be decidable. For every, there's a lot of things you can decide, but not everything, not all claims. And boom, you're not going to be able to prove simple consistency. You're not going to be able to assure yourself that your system is paradox-free just by plodding away. You're going to have to appeal to more complex systems in order to prove the consistency of simpler systems. Of course, the problem then is is your more complex system consistent? It's not a comfortable result, but it's thanks to the precisification, but getting precise about what exactly finitary approaches were. It's proven. So if you buy the Church-Turing thesis, that's what humans aren't ever going to be able to prove the consistency of arithmetic just by churning away, writing one thing after another. They're going to have to appeal to sort of concepts that are larger than arithmetic, more complex than arithmetic. I thought it might be interesting, in the absence of any questions, or while you're waiting for questions, I'm waiting for questions, to just show you what an axiom set looks like. To just make it clear, it's not finite. It's finitary, but not finite. So here's a set of axioms for arithmetic. Remember, the upside down A's mean for all. So the first axiom says that for all x, and the x with a little, what do you call it, apostrophe above it, means the successor of x, so x plus 1. So for all x, there's no, 0 has no, there's no x that is the 0 minus 1, because this is just for the natural numbers. 0 is the start, if you like. And then for any natural numbers x and y, if the successors of x and y are equal, then x equals y. So the successor doesn't branch out. It's just one line of numbers. Then for all x, if x isn't equal to 0, then there's a y such that x is the successor of y. So apart from 0, all other natural numbers have a predecessor. Then you have some axioms to define addition and multiplication. So that's all, they're all just straight, boom, axioms. So far, it's a finite set of axioms. There's 1, 2, 3, 4, 5, 6, 7. But then for induction, you need an axiom scheme. So for any formula, for any property, if you like, that you can define within the language of arithmetic, if you can show that that property is true for 0, and the v, the upside down v, is an and. So if you can show the property is true for 0, and you can show that for all x, if the property is true for x, then it's true for the successor of x, then you can conclude that it's true, the property is true for all x. So that's a scheme. That's actually an effectively enumerable. Well, so long as you've got a list of properties, you can effectively enumerate from that list all of these, each instance of that axiom scheme, because you just plunk in each property. And if you're given an axiom that looks like the axiom scheme for induction, you can check whether or not it is a true axiom of induction by going through your list of properties one by one and seeing if you substitute that property into the axiom scheme, you get the one that you're looking at. So that's the idea of effectively enumerable, or effectively checkable, that you might have an infinite number, but you can line them all up in a list and go through them systematically one after the other, and you know eventually you'll get to any particular one you're after. Okay. Any questions yet? I thought oh, NP, yeah, okay.
I want to ask a lot of questions on that because I think Georgia gave us the wrong definition.
Well, there's lots of different definitions, Hyang, but I'm happy to go over it again.
Eric, are you ready to ask? This is your last chance to ask about the NP class problem. Eric, are you there?
How about I go through and maybe I'll say something, I'll give you my take on it, and oh, well, do you want me to? I can give you my take on it and you can stop me if there's anything you want clarification on. Hello? Okay, so the original definitions were in terms of Turing machines, yeah? But really Turing machines are just a sort of an abstract way of talking about what we call, a digital computer these days. So you can do the same with an algorithm that you do with a Turing machine. But let's talk about it in terms of Turing machines. So first of all, P and NP are actually only defined for decision problems, yeah? So that's problems that take some input and then just say yes or no. Okay, so the thought of is that the set of decision problems that are on all inputs, the number of transitions of the Turing machine that will be required to reach a decision. No, not optimal problems. No, only decision problems for P and NP. That's a key thing to grasp. Okay, so the thought is the original definition was all those decision problems that you can write a Turing machine for that will give you an answer for any of its defined inputs. So it'll halt in an accepting state or a rejecting state in a polynomial number of transitions. So, you think of your Turing machine is going beep, state 1, beep, state 2, beep, state 1, beep, state 2, beep, state 1, beep, state 4. It's popping from state to state as it reads and moves around on the tape. So if you count up, you get the...
Wait. So polynomial. So the P class problem is only works for the decision problem, right?
That's it. That's what it's defined for.
So I will just change the definition.
Yep. P problem. The original definition was it's a problem, a decision problem for which there exists a Turing machine that will halt on all inputs in a number of transitions that is bounded above by a polynomial function of the length of the input string.
Okay, and what about NP complete?
Okay, yeah, well, okay, so has everybody got that straight? And then it's actually, because you can translate a Turing machine into an algorithm in polynomial time and vice versa, that sort of turns out the same as an algorithm. So a P by extension, you can just say, you can forget about Turing machines, and just because actually they're horrible if they do anything interesting, they're so complicated. You think about algorithms, it's the same sort of thing. P problem will be a problem for which there's an algorithm that will, a decision problem for which there's an algorithm that will solve that problem in polynomial time. It's where the time is a polynomial function of the size of the input. Yeah. Oh, well, then it's not an NP complete problem. Okay, hold on. Okay, so then we have the NP problems. Yeah. Where if it's defined right, these include the P problems. So P is a subset of NP. The NP problems are, originally the definition was, it's a non-deterministic polynomial time problem. The non-determinism is normal Turing machines, when you have the state transition function for a state where you're reading a particular input, there's only one place the Turing machine can go, yeah? If it's in state 3 and it's reading an input 1, then the transition function says, go here, and that's it. A non-deterministic Turing machine, you can also define a non-deterministic Turing machine, and in a non-deterministic Turing machine, there might be several different states that the machine can go in on a particular input and state. Yeah. So I guess if you think of it, a non-deterministic Turing machine, can branch. So in state 1, input 1, it doesn't just go one place. It could go to state 3. It could go to state 9, 10, 100, state 9, and state 6, yeah? And then that could, then again, it can have, the transition function. It's not a function, sorry, it's a transition relation, because it might be, have many options. So you can think of that as, it's sort of a bit like parallel processing in a way, isn't it? It's branching. And you say a non-deterministic Turing machine accepts an input if on one branch it halts in an accepting state, yeah? So the thought is that, how does that work when you're thinking about algorithms? Well, remember, NP was like, you can't find the solution in polynomial time, but you can check a given solution to see if it's right in polynomial time. No, because what that's meaning, if you think about the Turing machine that's sort of branching like this, so, or if you like, every time there's an option, it splits into 2 Turing machines, or 3, and each of those goes off down its path. So, the transition function offers 5 options on a particular state and input pair, you can think of that as then the Turing machine splits into 5 Turing machines, and each of them keeps going. Yeah. So can you see how you can get, a factorial increase in your number of exponential increase in your number of Turing machines in a way there. So that's the NP thought, is that you are splitting up the processing, but once it halts, all you've got to do is trace back that arm. So even if this halts here, the Turing machines split into lots and lots of little Turing machines, but one of them has halted. And once that one halts, to check that it's halted properly, to trace back its particular arm of the tree, if you like, is still just a polynomial thing. So that's what NP is. It's like, okay, you may not be able to find the solution on just one little Turing machine that's going ping bonk, ping bonk, ping bonk in polynomial time. But if the Turing machine is allowed to clone itself, as it were, and split, one of the Turing machines will find the solution in polynomial time. Or if you prefer to think of it going back up the tree, you can check that solution in polynomial time going back up the tree, because it's just going to be a polynomial length branch. But there's going to be a lot of branches, maybe. Is that making sense?
Kind of making sense to me,
yeah.
But for this graph, shouldn't we draw a dotted line on P, just show that P doesn't equals to NP?
Well, if you're thinking of it now, like NP is solvable by a non-deterministic Turing machine in polynomial time. A deterministic Turing machine is just a special case of a non-deterministic Turing machine, namely one where it just so happens that there's only one option for each state and input pair.
Wait. What is the non-determined Turing machine?
That's what I was saying. And so a Turing machine, normally, you're given a state and a state J, say, and an input read. Oh man, this is such an annoying system. Sorry, not this. Okay, and an input read, say character, say QJ. And then you've got this transition function, yeah, which we call little delta for some reason, because for change, I suppose. So it says, the transition function says that give me a state and an input, and I'll tell you a new state. Let's call that state ij, because you'll be looking up a table. The jth state for state I, input state I, and character qj. A new a right character ij, and a direction to move, yeah? And, left or right. So a triplet.
Yeah, and then that's a deterministic Turing machine.
Yeah. Okay, so that's what that says. It's deterministic because the delta here is a function, yeah? You give it a particular input, it only gives you one output. In a non-deterministic Turing machine, delta is not a function. So it might give you, there'd be several. Or or just like square root of x. Well, of course, square root of x isn't a function.
Yeah.
Well,
I understand.
plus or minus, because it gives you two options for each X. Yeah.
No, I understand. So like,
Yeah.
just
So in a non-deterministic Turing machine, this delta isn't a function because it can give you several possible options for each input
it's
pair.
one situation will give you different output depends on the choice, right?
Well, yeah, you can describe it different ways. You can say it gives you different output, or the Turing machine has a choice of which one to go on, or you can say that it splits and two little Turing machines or several little Turing machines follow each course, or it doesn't really matter because it's maths. Really, these are all just ways of imagining it. The maths is just it's a relation, not a function. And the thought is that the machine will accept an input if there's one defined sequence of transitions that leads to a halting state, a halting accepting state. So you can think of that as like a tree. The Turing machine, every time it has a option of which state to go on, that's like there being several branches from the state and input that it's on. Yeah?
Yes.
Okay, so
You make a non-deterministic Turing machine program.
yeah, it just has several options for each state and input pair.
I know, but is that possible for a human to create a non-deterministic Turing machine? I know we could just create a deterministic Turing machine by the making the program. I mean, like computer is a deterministic Turing machine, but what about non-deterministic? Is that possible for a human to create one?
Oh yeah, hey, hang on a sec. We're talking complexity now, not computability.
Oh,
In terms of computability,
both of them together.
you can always turn a non-deterministic Turing machine into a deterministic Turing machine. You just turn it into a Turing machine that goes down every branch. Yeah? One after the other. It's a bit like turning recursion into iteration. But, so they're both computable. Yeah? So your laptop could emulate a Turing machine, and it could also emulate a non-deterministic Turing machine. But it would take a lot longer to emulate a non-deterministic Turing machine. That's the whole point of NP, yeah? So there's computability, and that's defined by being computable by a Turing machine. And it could also equally well be defined as computable by a non-deterministic Turing machine, because in terms of computability, they're equivalent. But now we're interested in complexity. That's, how feasible it would actually be to compute. So there's in principle computability. But now we're thinking about, well, what actually, in a decent amount of time might you be able to compute? And the thought is these are two separate classes then, because the polynomial number of transitions is a whole order of magnitude different, probably, from the non-deterministic polynomial transition. Well, that's the big question. Yeah. Okay, so I'll move along because we're going way over time. Not that I care really, I suppose, but people might get bored. Okay, the big thought is that given a particular solution to a problem by a Turing machine, Well, given a particular problem, you can turn it into another problem. It's often possible to turn, if you've got a problem, say, well, what's an example? If you want to know if there's a traveling salesman, so the traveling salesman decision problem is there a circuit through this graph of less than a particular cost? Yeah, yes or no? Okay. Now, there's also the Hamiltonian circuit problem, which is just, is there a circuit of this graph that only goes through each, is there a tour of this graph that only goes through each node once? Okay, so if you're given a particular graph and you ask the Hamiltonian problem, if you already have a Turing machine that will solve the traveling salesman problem, you can just use that, yeah? You can turn the Hamiltonian circuit problem into a question for the traveling salesman machine. How? Well, you just give every edge the value 1 in the graph, and then you ask, which will only take, however many was bounded above by a polynomial function of the number of nodes. So you can do that in polynomial time or better. And then you ask the question of the traveling salesman Turing machine, is there a circuit of this graph of cost less than, what is it? Is it n minus 1? I think, off the top of my head. But the point is that idea that if you have a program that solves one particular problem, often you can use that program to solve other problems by translating the other problems into the problem that your program solves. That's called reducing one problem to another problem. That's the key idea here, yeah? So we can say, well, within NP, there are these group of problems. Oh, man. Let's call them these ones here, that are NP complete. How? Well, because they're the kind of problems that any other problem in NP, we can design a polynomial time Turing machine or a polynomial time algorithm that will turn that problem into the sort of problem that an NP complete problem can solve. So if we've got programs for these ones, the NP complete ones, we can solve all of the ones in the whole of NP just using those programs. The only other programs we'd have to write are little programs to translate the other problems into NP complete problems. Hold your horses. Okay, so that's the key. This is, maybe if I do another. NP hard. So the key concept here, apart from the non-deterministic and deterministic Turing machines, the key concept here is the concept of being reducible. Let's call that arrow, is reducible in polytime too, yeah? Okay, so, and basically, that means it's a bit like saying is easier than. Yeah. So Hamiltonian circuit problem is easier than the travelling salesman problem because you can, given any question about a Hamiltonian circuit for a graph, you can turn that in polynomial time into a question about the travelling salesman problem on that graph. Yeah. Okay, so then let's draw a few blue arrows. So P is reducible to NP, yeah?
What do you mean by producible?
Reducible?
Reducible. P is
Okay.
reducible to NP.
If given any polynomial time problem, you can question, given a question about something that's solvable in polynomial time, you can turn that in polynomial time into a question about something that's not solvable in polynomial time.
I will ask: are all NP complete problems are in hard?
I didn't understand that. Sorry.
Are all NP complete problems are in NP hard?
Oh, just hold off on the NP hard for a sec. We're not got there yet.
And all right.
Okay, so then that's just sort of obvious. Polynomial time problems are pretty easy problems, and you can, if someone came along to you with a polynomial time problem, you could just solve it, which is probably what you do. But you could go, oh, I can just convert that in polynomial time into a travelling salesman problem and then use my travelling salesman program to solve it, which would be stupid because, the travelling salesman program will probably take ages. But you could do it. That's the point. Is reducible in polynomial time too is sort of saying is easier than. So polynomial time problems are easier than NP problems, yeah? Now, NP complete is defined as given any problem in NP, you can reduce it in polynomial time to an NP complete problem. So if you've got a program that solves travelling salesman, the travelling salesman decision problem, you can use that program to solve any other NP problem, is the idea. By turning that other NP problem question in polynomial time into a question that's about the travelling salesman decision problem. Maybe a better one would be the satisfiability problem, because that's one of the main NP complete problems. Now, the reason why they did that basically is because, why you got this definition is because, of course, if you could get a polynomial time sorry, I blew that. If you could get I meant to draw that into P. If you could get an NP complete, oh, beauty. If you could get an NP complete problem and write a, so I'm fighting with the software here. If you get an NP complete problem and write a polynomial time program for it, you'd have effectively reduced all of NP to P, yeah? Because you could use that polynomial time problem to solve any other, you could turn that into a polynomial time solver for any other NP problem, because all the NP complete problems, all the problems in NP can be polynomial reduced to an NP complete problem, and then you've reduced that NP complete problem to a polynomial problem. So two polynomial time programs put together is still polynomial time. So given any NP complete question, any question about an NP problem, you could turn that in polynomial time into an NP complete question And then you could turn that NP complete question into a polynomial time solvable question. So you could do it all in polynomial time. That'd be lovely, wouldn't it? But so that's why this definition of what's reducible to what. But it probably doesn't exist. So there you go. Okay, NP hard problems are such problems that you can reduce NP complete problems to. And here's the thing, generally speaking, when they talk about NP hard, all bets are off. It's not a decision problem, it's just any blooming problem. So, for instance, the travelling salesman decision problem, is there a travelling salesman circuit for this graph of less than 10, of cost less than 10, say? Well, of course, that's reducible to the optimization problem, because you just say, oh, well, what's the cheapest circuit on this graph? I mean, the cheapest tour on this graph. And then, is it less than 10? Okay, we've solved the decision problem. Okay. So NP hard problems oh, sorry. I think I've done it the wrong way.
So NP complete is reducible to NP. NP hard is reducible for NP complete, right?
I'm sorry. I think I've got my arrows the wrong way around, haven't I?
Yes, you got the way around.
Yeah.
But by the way, you are also right in some way, because I suggest that it's the food chain. It looks like this. Which one is bigger? Which one you point at? That's the food chain.
P is easier than NP. It's complete. Yeah, sorry, I did the last arrow the wrong way around. It should be like that. It's like that. Sorry. So NP complete problems are reducible to NP hard problems. So NP complete problems in general are easier than general NP hard problems. But NP hard, the key thing is that NP hard doesn't have to be decision. It's just talking about all algorithms now. Shall we go now? Anybody got anything further to say?
I think I understand now.
Cool. I'm glad to hear it, Kevin. It's an important life skill. Okay, doke. Have a good weekend. Arrivederci. You can always send me an email if you want to. If something comes up and you want to chat about it, I'm open to discussions, one-on-one, or several on one, or whatever. Okay. Bye.